In this section, we're going to look at a different kind of combinatorics question. An example of the type of thing we're going to look at is the following. We're imagining that we're looking at all second-year computer science majors, and we want to figure out how many there are. But we don't actually have that information. Instead, we have information about what courses they take. So we know that if you're a second-year comp sci major, then you have to take at least one of the following 3 courses: algorithms, logic, design, and compiler construction. So this means that every student is definitely taking one of those, but some students might be taking more. And we have information about the class lists. So we know that there are 75 people taking algorithms, 60 taking logic, and 50 taking compiler construction. So that was just if I looked at the class lists for those 3 courses, I'd see those numbers of students in each course. But as we said, some students can take more than one course. So if we imagine we have the information that tells us that actually 10 of them took all 3 courses, 25 took algorithms and logic, 12 took algorithms and compiler construction, and we have 15 took logic, design, and compiler construction. And from all this information, we want to be able to figure out how many second-year computer science majors there were. Okay, it might seem like a bit of a strange question, but this is what we're looking at. So far, we've really been using the rule of products for our combinatorics. But if we have a look at the rule of products, it's really not going to help very much. It talks about operations or choosing objects, and that's not anything really that we can model our non-disjoint class question with. So we can't use this, and since our permutation counting algorithm is dependent on the rule of products, that's not going to work either. So we need some new stuff. The first concept that's going to be useful for us is the idea of a partition of a set. So let's read through the definition and see if we can figure out what it's talking about. So a partition of a set is a set of one or more non-empty subsets. Okay, so a partition, before we go any further, is a set of sets. And then there are some conditions on those sets. So the first thing to notice is any of the subsets must be non-empty. If we carry on reading, such that every element of A is in exactly one set. Aha. So this is saying we're dividing A up into a bunch of sets where each element of A lives in one set and one set only. So there are no intersections. Symbolically, we can put this as 2 conditions. Firstly, our set A is given by the union of our subsets, which is part of saying every element of A is in one of the subsets. But to get the exactly, we need to say, well, if we have 2 subsets that are not the same subset, then their intersection must be the empty set. So we don't have any elements that are in 2 different subsets. So this is the definition of a partition. I think it's helpful having a kind of mental picture. The way I think about it is I imagine that I have some overall set A, and when I partition it, I'm breaking it up into sections that might look all different, but there are no intersections, and if I look at the union, that gives me the whole set. So this is a little bit different from our usual Venn diagram, but I find this is quite a useful mental image. So let's look at some practical examples. So here's our set A, and it's given by 4 elements, A, B, C, D, and we can make up some partitions. So, for example, we could say, so remember a partition is a set of sets, and we've got to have every element in it. So I'm making a singleton set with A, and another set with B and C, and another set with D. And that's an example of a partition. Let's just check. What does it mean to be a partition? Well, to be a partition, and it's useful to just have this checklist in your mind, you need to be a set of non-empty sets. Okay, so we need to make sure that it's non-empty. We need to make sure that the union of our subsets gives the whole set. And the third thing is that our intersections are empty. So that's just kind of my mental shorthand for remembering what a partition is. So if we go back and check, is this bunny over here a partition? Well, we're checking non-empty. Are each of the subsets non-empty? Yes. Does the union give us the whole set? Well, if I take the union of the set containing A and the set containing BC and the set containing D, then yes, I get the whole set. And then the final thing to check is our intersection between any two of the subsets empty? Well, if I look, intersection of A and BC is empty, A and D is empty, and BC and D is empty, so yes. So this is a partition. So take a moment for yourself, pause the video, and see if you can come up with a couple other partitions for this set. So here are two that I think are worth looking at. Firstly, you can always partition a set into the set of sets containing each element as a set. So that's a perfectly good partition. And you could also partition a set into just one ginormous partition, which is the set itself. So if you think about what I've done over here, I've got A, B, C, D in my whole set, and I've partitioned my set like that. And over here, I've got my whole set, A, B, C, D, and I'm thinking of the whole set as the partition. But it's still a set containing a set when I talk about the partition. So as we've talked about before, it's useful to look at some examples that are not partitions because they fail in some aspect. So remember, we've got our three things that we need to have true in order to be a partition. Let's think of an example which breaks this definition. So for example, if I put a set containing A, B, C, D, and the empty set, that's not a partition because we require that every set in our partition is non-empty, and this is the empty set that I've included here. So this is not a partition because it contains empty set, the empty set. Okay, now let's see if we can find an example that breaks our definition that requires that the union gives us a whole set. Well, we could have a set containing AB and the set D, and this is not a partition because the union isn't the original set A, because we're missing C. And then finally, we want to find an example that breaks our intersection being empty requirement. So for example, we could take the set containing the set ABC and also containing the set AD. And again, this is not a partition, but this time it's because the intersection of the two sets in our partition is non-empty. So we have a non-empty intersection. So it's worthwhile playing around with some more examples for yourself, just to get a feel for what a partition can look like and what a partition definitely isn't. So you might be wondering if we can partition infinite sets in some way, and we absolutely can. Let's look at an example using the integers. So here's a partition of the integers. I'm going to create a set of sets, and notice that I'm actually using set builder notation to build my set of sets. And I claim that this thing is a partition. So let's think about what this is. If I want to write this out, well, it's the set of all sets of this form where n is an integer. So I'm going to have -2 will be a set, -1 will be a set, 0 will be a set, and you can see how this is working. So the question then is this actually a partition? And we want to just check. Firstly, we need to make sure that none of the subsets that we've picked are empty. So let's just do our check. Non-empty, yes. The next thing we need to do is check if we take the union of all of these bunnies, do we get the integers? Yes, we do. And finally, we want to check that our intersection is empty. And if we have a look, we see that by this definition, yes. So this is a possible partition. And in fact, it's what we would call the finest partition. You can't break the integers up into a partition with more little bits than this partition. So here's another partition. We're going to have a set which contains all the integers that are strictly less than 0 as one of the bits of our partition. We're going to have the set that contains 0 as one bit of our partition, and then we're going to have the set of all integers where n greater than 0 as the third bit. So we've partitioned the integers into 3 blocks. Let's just check that it is actually a partition. So we need to check that each of our 3 blocks is non-empty. Well, we definitely have at least one integer in our first block, for example, -1. We know that 0 is in our second block because that's what we've said. And if we think about our third block, well, we definitely have an integer in there, for example, 42. So it's non-empty. If we think about, does the union of our 3 blocks give us the integers? Quick check will see, yes, we do. And finally, we can also check the intersection and see that that is also correct. So this is also a partition. So let's look at some examples of sets of subsets of integers and decide if they're partitions or not. So just take a moment for yourself, pause the video, and see if you can figure out whether they're partitions or not. If they're not a partition, explain why not. So which of the 3 conditions required by being a partition are violated? So if we just do a quick check through, so I'm looking at the first one, and again doing the usual check, we want to check that our subsets are non-empty. Let's have a look. Well, yes, that looks good. There's definitely an integer in there, for example 5. There's definitely an integer in there, say -1. So they're fine for being non-empty. Let's check the union. If I take all the elements in here and all the elements in there, yes, I get the integers. And then how about intersection of our 2 sets being empty? Aha! Now we see that these 2 blocks have in common the element 0. So 0 is in that set, but it's also in this set. So we don't have a partition because the intersection of our two blocks is non-empty. If we have a look at the next example, so let's think again. Let's check non-empty. So it might be helpful to write out exactly what this looks like because it feels a little bit complicated. So we've got the set of sets where each set consists of those elements of n where the absolute value equals k, and k goes from -1, 0, 1, 2. Okay, so starting with k is equal to -1, we've got the set of n whose absolute value is equal to -1. Well, there aren't any integers whose absolute value is -1, since an absolute value is always positive, so this first set is empty. Let's just keep going so that we can check that we've got the right idea here. Now we want the set of all n whose absolute value is equal to 0. Well, that would be 0. Now let's have a look. We want the set of all n whose absolute value is equal to -1. So integers who, if you take their absolute value, gives you 1. Well, obviously 1 is one of those, but also -1. And we can start to see the pattern if we look at the next. When k is equal to 2, our next block will be -2, 2, and so on. So don't be afraid to actually just write out the elements in a set of subsets like this, because it can be tricky to do it without. So now let's go back to our check, and we see we fail at the first hurdle because this can't be a partition because it includes the empty set. And so we're done. So just to pull this all together and make a couple of points absolutely clearly, you'll have noticed that I've sometimes been calling the subsets in a partition blocks, and this is standard terminology. Other things to notice: we can use the definition of partition to take an infinite set and partition it. We saw that with our integers. And we can partition an infinite set into an infinite number of subsets. So we also saw that. The thing to note is that if you have a finite set, obviously you're not going to be able to partition it into an infinite number of subsets because you're limited by the number of elements that you have.